exponential growth, decay, and solving functions. In the first three problems, they want us to identify the initial amount A. So I'm going to do that for each one of these. The first one is 220. The second one is 5.5. The third one is 1. Now, if you're not sure how I did that, the idea is that all of these follow our parent function of y equals a times b to the x power, where a is our initial amount right there. And so if you're like, well, this one doesn't have 1, yeah, it would have to be 1. 1 times 2.5, because b would be 2.5 here. And then next is the rate of growth r. Well, okay, so I did draw this. However, these functions kind of follow this. It's a times 1 plus r to the t power, where this portion, I went with blue, so here, this portion is where the rate is at. So what we're going to look at is like this one right here, 1.015. Well, so then the rate would technically be 0.015, which is 1.5%, because it wants it as a percent right there. The next rate would be 0.5, which would be 50%. And then this one's kind of interesting. The rate is 1.5, which would be 150%. If you're wondering how I'm doing that, so imagine we have this 1 plus r. Well, what if we said, okay, 1 plus r is equal to 1.015? So you would subtract 1 from both sides, and then the rate would be equal to 0.015, right? That is what we did down here. And then next it says evaluate. Let's underline that one. Evaluate the function when t is 5, round to the nearest tenth. The only way to do that for these is go get a calculator, plug it in. Desmos is mighty nice to do this with. And so I've already done that. This is 237.0. This one is 41.8. And this is 97.7. And no, I didn't take the time to show you how I did it in Desmos, but just trust me, that's what it would be if you plugged it in. Write a function that represents a situation. So the functions are going to look like this. So there's our initial value, basically 1 plus r to the t power. That's what this one and this one are going to look like. So what we have is y equals a college tuition of $135 per credit hour. So that was the initial cost until it increased. So 1 plus 0.05, because that's how you write 5% as a decimal, to the t power. And we are done. That is the answer. Now on the next one, we have y equals a bee population of 3,000. That's what it was before it increases by 40%. And then this every year part is not really relevant, same as up there. So it's 1 plus 0.4 to the t power. Just like the top, we are going to identify the initial amount. So our initial amount here is 1420. Our initial amount here is 1, again, because it's there in front. And our initial amount here is 9.2. Next, we have the rate of decay r as a percent. So the rate here is going to be, let's see, 0.105, which would be 10.5%. The rate here is going to be 2/5, which is 40%. And the rate here is 2/3, which is 66.6 repeating percent. And then now we want to evaluate the function when t is 3. Just like earlier, you go to a calculator, you plug these in, And what do you plug in? You plug in a 3 there, there, and there. If you didn't see me do that, there, there, and there. I guess I didn't point that out up here. You're going to plug in the 5. Remember we said 5. You're going to plug it in here, here, and here. If you didn't see it, here, here, and here. Let us go down here. Again, I already did this in Desmos, so I am not going to like take the time to show you how to do that, because you can type in, an answer. You can type in an equation, and then you'll just put that 3 up there. So that's that. 9 and 10, write a function that represents the situation. Basically, so here, we drew arrows up here. Let's draw arrows down here. So it goes here and here as well. There's not going to be any type of compounding interest, so don't worry about that this time. So we have a car. That's what we bought it for, and it decreases in value by 16.7% each year. Well, that's going to be 1 minus 16.7, which is going to be 0.833 to the t power. Next, we got a company's annual review of that much money, and it decreases by 4.2%. So that's going to be 1 minus 4.2%, which is going to end up looking like this, 0.958 to the t power. And if you're like, I don't really get how that works, let me write out the detail to the right. 1 minus 16.7% is really 1 minus 0.167, and that's how we get that there. And then same thing here, 1 minus 4.2% is really 1 minus 0.042. And so you can see, like if we were to add 0.042, this would all round back up to 1. And if we were to add back in 0.167 right here, we would get back to 1. Let me see. I didn't need to show that probably as much. Actually, I didn't really show it, the final product right here. So that's kind of funny. If you did write the final product, I guess it would look like this. Y equals 135, 1.05 to the t power, and y equals 3,000 to the 1.4 to the t power. So that's what those look like. I mean, I think you could have figured that out. And I guess I also could have written these in the parentheses. And if you're like, what do you mean in the parentheses? It would have been connecting back here. This would have been back here. Okay, next page. Determine whether these are exponential growth functions, decay functions, or neither, and explain. So this first one, this is going up. Let's change colors. I'm not a fan of the bright blue. There we go. Only use it to point stuff out. It's going up by 5. Going up by 5, going up by 5. That is going to be a neither. It's neither exponential growth or decay because it's linear. I mean, it has a slope. It's rise 5, run 2, right? So, because it's going up by 5 there, it's going up by 2 there. So, no thanks. So now here we've got, let's see, that's 12. That's 18, and what is that, 27. I guess I'm writing subtraction, but really we're going the opposite way, aren't we? So minus 27, minus 18, minus 12, and then this is going by 4, by 4, by 4. So we're fairly okay with that not being linear, right? Because it's not an exact slope each time. So let's go back and see what happened here. One thing I like to do when I can't just figure it out is go, okay, 81 got multiplied by a number. You could do 81n, you could do 81x, I don't really care. And that's going to equal 54. So now we'll divide by 81, divide by 81. You get that x is, let's see, this is divisible by 9. That's 6. This is divisible by 9, and you get 9. And we divide by 3, and also, so we would get 2/3. So 81 times 2/3 is 54. So let's see, is 54 times 2/3, does that equal 36? Well, let's find out. 3 can go into 54 18 times, and yeah, 18 times 2 is 36. So it would appear that we have, it's going down 2/3. So this is going to be decay, and it's because of it going down 2/3. I guess you could say, you know, that the rate that R is equal to 66.6 repeating percent. You know, because 66% is what 2/3 is, right? Next, the table shows the total number of shares of an initial public offering purchased T days after it opens on the stock market. Determine whether the table represents exponential growth, decay, or neither. Okay, same thing. So here it's a difference of 600, a difference of 1,500. I mean, we can pretty much stop there to go, yeah, this is not going to be linear. So I notice over here, I started on both of these, actually, I started like with the subtraction of the smaller numbers. That's fine. And just another thing to kind of make my math easy on me is I'm going to do 1,000x. So here, yeah, I'm starting there. 1,000 times a number, x, is equal to 400. So I divide both sides by 1,000. Divide by 1,000, and I get that x, so that cancels, x is 4/10, which is 2/5. So at least from here to here, if you multiply by 2/5, that's what you'd get. So let's double check. If 2,500 times 2/5, would that equal 1,000? So 5 goes into 2,500 500 times, and 500 times 2 is in fact 1,000. So we're pretty sure that what's happening is it's decaying, and the rate is, now you could say 2/5, which is 0.4, which is 40%, by the way. How many shares were purchased after the stock had been open for 6 days? So here's the thing. You have two options here, and one of them is a little more complicated than the other. One is just fine. So here's the thing. We have a table, right? We have this table. We don't have the initial value. The initial value happens when t is 0. So what's my point is we don't have a function yet. So do we have a function? Not yet. ... Frowny face. So we could come up with a function. I'll show you that. But I think maybe the easier route here is, say, let's take 400 and multiply by 2/5, and this is going to represent day 5. Okay? So what we end up getting is 5 goes into 480 times. That's 160. Take 160 and multiply that by 2/5, and this will represent day 6, which is what we're after. So check this out. 5 goes into that, let's see, 32 times. 32 times 2 is 64. So after 6 days, it's worth 64. Hang on, that's what it's worth? The number of shares of an initial public offering purchased. Ooh. So yeah, after 6 days, only 64 purchases have been made. I don't know if you have any feelings about what the heck that means or not, but there we go. They're not buying many shares. So now, do you want the function version? I'll show you if that's what you are interested in. So here's how you find the function version. What I'm going to do is I'm going to say, I'm going to take 6250. that is the amount of shares sold on day 1. So I don't know our initial value. I know this is going down by 40%, and I know on the first day, like I said, we had 6250. So what we could do is when we simplify this is just 6250 equals 0.4a. Divide both sides by 0.4, and we get 15,625. And so in that way, we can write a function for this. 16,000, what did I say, 625? No, 15,625. So y equals that, our initial amount, times 0.4 to the t power. So this does represent our table, but I don't care, right? The reason I don't care is because I found this to be very fast if you thought of it. If you didn't think of it, then you actually have to think, well, let's see. I don't know this amount. So, in fact, here's how I came across, like, how I would have done this. Normally you have this, right? And we already knew. So here's the things we knew. We knew y on day 1. That's one thing we knew. We knew t, and we knew that when t was 1, and we know that the rate is actually, so I guess you could say it was, minus point, say, hang on. So let's change this. Let's change this to just say, let's just say that was b, okay? Instead of like talking in terms of that. So we know that b is 0.4, okay? So when you know these things, you plug them in here, here, and here. When an equation has one unknown, you can usually solve for it. Well, you can hopefully solve for it, because then you can know what it is. And that's what I'm saying. We found out that a was equal to that. That was our initial value, which gives us this. So that if then you were to go to Desmos and take a 6 and plug it in here, you would get 64, I promise. Alrighty, we're going to rewrite the functions to determine whether they represent exponential growth or decay. I guess really the focus here is that we're just rewriting forgot to select a pen. We're going to rewrite the functions. I mean, yes, we kind of determined in class that you could just pretty much look at these and still say, yeah, that's decay, that's growth, but let's rewrite them. And we took a timeout in class to do stuff like this. So if you're not familiar with that, go back and check out some of those notes, or ask me where those notes are, and we can go look at them. But here we go. So we have y equals 0.3 to the t minus 2 power. What that's going to look like is 0.3t over 0.3 squared. Why is that? Because when you have the like bases of the 0.3, and when they're dividing each other, dividing like that, then you can subtract their exponents. So like it would be t minus 2 like that, and that's obviously what we have. So you can either grab a calculator, or you might know what 0.3 squared is. It's 0.09. And so what that means is we have y equals 0.3 to the t power over 0.09. And this is one we did in class that it felt a little funky to them. But here's what I did, is basically I said, hey, listen, this bottom part, it's as if we have 1 over 0.09 times 0.3 to the t power. And really to kind of complete that, if I did that, maybe that's the one thing I was missing in class, is I didn't put that over 1. But if you think about it, this could technically be split up into 2 fractions, multiplying each other like that. And so now I do have a calculator up. 1 divided by 0.09 is 11.11 repeating. So this is y equals 11.1 repeating times 0.3 to the t power. And then, yes, of course, I guess we should go ahead and say this. Yes, this is decay. But the point was we rewrote and got this function right here from the original function right here. Now we have y equals 3 times 1.6 to the 4th power raised to the t power. And if you're confused on why that happens, this is 4t, and when you have a power raised to a power, you multiply those powers. So again, I got a calculator here. 1.6 to the 4th power is going to be, so here, hang on, let's keep that 3. It's going to be 6.5536 to the t power. I mean, we could round that, but I mean, leaving it like that's pretty okay. So that's it on that one. We're done. Yes, that is growth because 6.5 is definitely bigger than 1. And the next one, we're going to have y equals 9 times 0.68 to the 1/3 power, and that is being raised to the t power. Again, how is that? Well, if you have a power raised to a power, you multiply the powers, and 1/3 times t would be that. So calculator time, 0.68 raised to the 1/3 power is 0.879 blah blah blah. So it's 0.79 blah blah blah. So here's what I'm gonna do: 9 times 0.879 to the t. We don't have any instructions on how we should be rounding these, so I'm just gonna leave it like that, and we're done with that. All right, 1 through 10 here, we are basically just aiming to have the same base on all of these. And I kind of zoomed out and said, hey, at 1 through 10, we're doing something different because we're on 6.5 now, which is solving exponential functions. That's why up here this said, hey, it's growth, decay, and solving functions. So we just finished the growth and decay portion. Let's jump into solving the functions. So the deal with this is, hey, we have this 3 as a base, and we have that 3 as a base. That's the same base. So we can pretty much ignore them. Because if the bases are the same, the only way for this thing to truly be equal is if their exponents are equal. So now this is just solving. I'm going to subtract 5x to get 3x. Divide by 3 to get -2, and we're done with that one. Same bases, so ignore them. The exponents are equal to each other then. I mean, they would have to be if this thing's going to be equal. Subtract 5x to get -3x is 3. X equals -1. 8, 4, not the same base. In fact, we're going to have to change both bases. We haven't had to change any bases yet. So really, fun times that we have to change them both. The thing is, most of these are going to be a change probably in this manner. A form of 2, 3, maybe 4, 5, and then -1. And if you're like, what do you mean -1? I mean the exponent of -1. So check this out. 8 is really 2 to the 3rd power, right? So there's an 8. So what we could do is say 2 to the 3rd is being raised to the 5x power. And 4, as you probably know, is really 2 squared. There's a 4. So 2 squared is being raised to the 4x plus 7 power. I don't know why these guys are so diagonal from each other, but this is what we're doing, right? So let me try and get them all on one line now, because we're going to have to multiply the exponents there. So we're going to get 15x, and that's going to be equal to, well, hang on. Yes, they will be equal, but I feel like I should do this 2 to the 15x is what this gives us. And then this is going to give us 2 to the 8x plus 14. How come? Those are multiplying each other, yeah? So now, this is where I started a second ago, say, well, 15x. Since the bases are the same, we basically ignore them, and the exponents are now what we're focused on. Subtracting 8x, I get 7x. Dividing by 7, I get 2. The answer is 2. I'll circle it larger. 2. The answer is 2. Number 4. Got to change both of them. I know this because 5 squared is 25. And I know that 5 cubed is 125. X minus 2 power there. 3x plus 1 power there. Multiply the powers to get 2x minus 4. And then I'm going to go ahead and jump ahead and just say equals 9x plus 3. Well, how do I know that's equal? Because now our bases will both be 5. And if the exponents are equal to each other, then they're equal. I'm going to subtract 9x to get negative 7x. I'm going to add 4 to get 7. And x is negative 1. 9 to the third power is 729. Fact. So 9 to the third power raised to the 3 times x plus 2 power equals 9 to the x minus 6 power. I'm going to go ahead and assume that, hey, we've got the 9, we've got the 9. We just need to make sure and multiply that, okay? So 3 times 3 is 9. So what we get is 9 times x plus 2, which is 9x plus 18, okay? Subtract 9x to get negative 8x. Add 6 to get 24, and x equals negative 3. Now, one thing I have not done is check my solution at all. And that is probably my bad. I probably should be doing that. So maybe I will go back and do that here at the end. I don't even know if you're going to watch it. It might be a giant waste of time. But you know what? The point is, if you were going to check your solution, then you would take this negative 2 and you'd plug it in here and you'd plug it in here. So, for example, we could kind of do this in our head, but let's suppose we zoom in and we go, oh, hey, 8 times negative 2, that's negative 16. And over here we go, oh, hey, 5 times negative 2, that's negative 10 minus 6. That's negative 16. So negative 16 equals negative 16. And I know none of us are going to run to the calculator to type in 3 to the negative 16th, mainly because we just proved that this is what we have. We have this on both sides, and then why would we check it further? So anyway, I checked several of these on my own because I accidentally started making an answer key before I actually did the video. So that's how I was able to kind of do a lot of these, perhaps, you know, a little quicker than usual. For example, knowing these answers without, like, going and grabbing the calculator, right? I already knew those because I already punched them in. Right here, just like the one above it, we're going to change both of our bases. So 4 is 2 squared raised to the 6 times negative x plus 2 power. And on the right, we get 2 to the third raised to the negative 3x minus 4 power. Got to be careful to multiply, so that's going to be 12 times negative x plus 2. This is going to be negative 9x minus 12. How did I get that? 3 times 3, 3 times 4, 9, 12. Okay? And then we didn't distribute the 12 here, but now we can. Negative 12x plus 24 equals negative 9x minus 12. If we add 9x to both sides, we get negative 3x. If we subtract 24, we get negative 36. And x is 12. Number 7. So we're going to have to change both our bases again. And now this is the first time that, like, check it out. Our entire assignment, I told you, it was going to be 2s, 3s, 4s, and 5s. So really, I was kind of wrong because we didn't do a single 4, and nor did we do a 3. We did 9. But by the way, on this one, we could have changed 9 to 3 squared, right? But my point in saying any of this is this one, number 7, number 8, and number 9 are going to deal with our buddy -1 as a power. So let's zip in here, zoom in here, wrong Z word. 8 can be rewritten as 8 to the -1 power. And that can be rewritten as 2 cubed to the -1 power. And that's really 2 to the -3 power. And then all along, outside of those red parentheses, was 2x plus 4. Like that. And then you would multiply those powers, and you get 2 to the -6x minus 12 power. And that is equal to 2 to the 4th power to the 4 minus x power. And then that is, I'm just going to bring it all the way down here, 2 to the 16 minus 4x power. Now, we have the same basis. We're going to ignore the exponents. I kind of went really fast over this idea right here because I'm thinking you remember or you know, yes, when I have a fraction or when I have a number, period, I can flip things over the fraction line with simply a negative exponent, right? So this purple 8 to the -1 is 1/8. That's just the truth. So, back down here. We are ignoring our bases, and it's just that the exponents must now be equal to each other, because if they are not, then we have the wrong answer. So add 4x to get -2x, add 12 to get 28. X is equal to -14. Here we go with 2/3 and 3/2. This one might trick you at first, because you think, well, crap, how am I supposed to make 2 into 3 and 3 into 2? Nothing like that. This left side is done. The right side is now almost done. So you see how this is now 2/3? Because this got flipped with our negative exponent, yeah? And you multiply the powers like that, so we get x plus 8 equals -2x plus 5. You add 2x, you subtract 8, and you get -1. Last but not least of the solving just like this, very similar. We have a 5 on top, but here is a power of 5 on bottom. Let's flip it. So let's leave this side alone for right now, and let's first flip this like that. And I will put this on the outside like that. And then now, here's where it gets extra fun. 25 is really 5 squared. 16 is really 4 squared. Oh, check it out. 5 and 4, right? Hang on, 5 and 4, right? Okay. Well, the fact that both of these are being squared means we could write it like this. And then don't forget, there was that -1 outside of it. And don't forget, there was that -4x outside of that. And now, check it out, we have a power raised to a power raised to a power. We can just multiply all of these powers. And so here's what we've got. On the left, we have 5/4 to the 3x plus 5 power. And on the right, we have 5/4 to the 8x power, right? Let's see. 2 times -1 is -2. -2 times -4x, that's positive 8x. Same base, we ignore them, and it's got to be 3x plus 5 equals 8x. Subtract 3x from both sides, we get 5 equals 5x, so x equals 1. Describe and correct the error in solving the exponential equation. So, fun fact, the answer is kind of cut off, so we will be solving this, I guess. We start right here with 1/16 and 64. So, I guess I wasn't a liar when I said, hey, we could be using a power of 4. You could also be using a power of 2, but 4 to the third power is 64. And in fact, they kind of start off how I thought. 1/16 is 4 to the negative 2 power. It gets flipped and squared. And then over here, 64 is 8 squared. That's true. But we do not have the same bases, so we cannot go to this right here. So the answer, the first answer is, what's the error? We can't do this yet because the bases weren't the same. So we need to make them the same. So on the left side, let's go ahead and deal with that, because I liked this, and this is 4 to the negative 6x power. In fact, that's how they got that. On the right side, it should be 4 cubed to the x minus 4 power, and that would become 4 to the 3x minus 12 power, where we ignore the bases and just set the exponents equal to each other like this. Subtract 3x to get negative 9x. And let's see, so x is really 12/9, which can be reduced to 4/3. This is a great time to go, let's check our answer. And here's the funny thing about this. I mean, yeah, I guess we probably should plug it in right up here. Don't really want to do that, but here we go. So 1/16 to the 3 times 4/3 power, that's what we got, is, well, here's what happens. Those 3's cancel, and we get 1/16 to the 4th power. Well, I don't know what 16 to the 4th power is. This is one of those scenarios where rewriting the base can actually help me to know, what the heck am I looking at here? So why don't I write it as 4 squared again? So 1/4 squared to the 4th power, that's really 1/4 to the 8th power. Okay, so now 64 to the 4/3 minus 4 power. Well, let's see, that's 64 and 1 1/3 minus 4. So that's really 64 and negative 2 2/3. I think so. And the reason I'm doing that is just because that was, I could do that kind of in my head. 2/3 plus 1/3 is 4. So now I'm going to rewrite that to be an improper fraction. So it's 64, and let's see, 3 times 2 is 6. 6 plus 2 is 8. Negative 8/3. Interesting. So let's come back over here, just because I need some room to think and write. 64 to the negative 8/3 power. Okay, well, that's 1/64 to the 8/3 power. Okay, one thing I like about doing these things, or dealing with these rational exponents, is 64 to the 1/3 power raised to the 8th power is how you deal with that. That's how you could calculate it without a calculator. And honestly, the challenge is to do that, right? So 64 to the 1/3 power, it would be so much harder to do 64 to the 8th power. In fact, here's what I'm talking about. It would be so much harder to do this. That would suck, especially without a calculator. So I know this part, that's the cube root of 64. Well, I told you 4 times 4 times 4, or 4 cubed, is 64. So check this out. This is just 4. And so now this was the left side, and the right side is going to be 1/4 to the 8th power. So we get 1/4 to the 8th equals 1/4 to the 8th. We were correct. Now, the reason that I went here to do this is because I did not do that on so many of these. And in my opinion, checking any and all of these would actually be kind of a piece of cake. 1, because they're all whole numbers. And 2, because you didn't... The original problem wasn't that bad. It was like going to be 2 to some power, right? whereas this one is, 16 and 64. The other thing that I would have liked to have done to check my answer was take 4/3 and plug it in here and here. That would have been so much nicer. But again, I chose the hard route just for the sake of choosing the hard route, okay? So, like, similarly here, like, okay, yes, here. 14, you could have plugged it in up here. That would have been kind of a pain. So, this one would have been sort of painful. But in theory, you could have also plugged it in right here, and you would have gotten the same thing. You would have gotten a solution that you would have been satisfied with. Now, solving these equations is kind of, for me, kind of a dorky fun thing because I get to graph. I get to just go to Desmos, and here's what I do. There's no way I can make this base of 4 and this 1/3 x plus 5. I mean, I underlined the 1/3, but there's no way I can make this interact with that 4. So here's what you do. You take this, and you say, hey, let's graph that. And you take this, and you say, hey, let's graph that. And you might be thinking, well, I don't like graphing to solve equations. I would rather do that. Well, guess what? This is how you're going to have to do this one. So you go to Desmos, you plug both of these in, and I'm going to do that now. All right, here we go. This is that number 11. And like I said, you type in one, you type in the other, and then you see where they cross. Now, one reason that I am interested to show you this one is that we have two solutions, which is possible, right? We have a curve and then a line. It's possible for them to cross. And something, that I found interesting was like, oh my gosh, it crosses at 15-0? No, it doesn't. It crosses at 15, and Desmos was like, bro, I'm not about to round. Or I'm sorry, I'm going to round to 0 because the number is so teeny, 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 tiny. Okay? Because we know this thing is approaching 0, right? So all we're interested in is the fact that x is equal to 15, way out there. And then the other x is, let's call it, do we have directions on rounding? No, we don't. So I, just out of personal habit, will do 3 decimal places, just out of personal habit. So there's the answer on 11. Let's go to 12 and 13, and we're doing the same thing now. We're going to graph each one. And in fact, I'm not going to write the y equals for each one. I'm just going to pause the video, go over to Desmos, and bring it back. Here we go. There was the 1/2 x plus 3, and notice mine says 0.2 because that's what 1/5 is, and it crosses at negative 0.797, and we don't care about what the y is because these will be equal whenever x is, let's say, negative 7.x equals negative 0.797. That's our answer for 12. And moving on to 13, 6 to the x power, 4 to the negative x plus 3 power. And you might think, dang, we're going to have to rewrite those bases. Remember, some situations you just flat out cannot do that. So you graph this side, you graph this side. Go into Desmos. Be right back. And here's the last one. Those cross two different curves. They cross when x is 1.309. Since I like to round to the third place just out of personal habit, that is the answer for number 13. Oh, just kidding. We got 3 more to graph. I'm going to graph. Okay, so as you can see, I have graphed all 3 of them. And let's zoom in here to check it out. These cross two different curves when x is equal to 2.377. 2.377. And if you slide over here, these never cross. This curve goes like this curve like this, and they never meet. So that's no solution. So yeah, that's kind of interesting that there's nothing you can do to make those work. A little bit of a giveaway, in my opinion, or just the giveaway is this is a positive 3. No matter what you raise it to, it's still going to be positive. This is a negative 4. When you raise it to something, it's always going to be negative. So anyway, same idea. And then over here, did I write down that? Yeah, I wrote no solution. And then over here, again, two curves. They do cross. And so it is when x is negative 4.226. Cool. Sweet, a bread problem. A bread dough doubles in size every hour. The volume y in cubic inches of the dough, x hours after the dough is prepared, is represented by this. When will the volume, which is that, when will the volume of the dough be 4,200? 4,200 equals 35 times 2 to the x minus 1 power. We can do a little bit of math. Right now, we can divide both sides by 35. I don't know what that is, but I got a calculator. 4,200 divided by 35 is exactly 120. So we get 120 equals 2 to the x minus 1 power. Now, again, we did one kind of like this on the notes, and I want to say it was like it was 500,000 or something. And so in the graphing of that, it would be kind of wild, or just difficult to see is what I think it really was, is like, listen, if the graph looks like this, 500,000 would have been like right up there. I mean, or technically there, but anyway, it made it difficult to see. So anyway, we're going to answer this by graphing both sides, because we cannot write 120 as a power of 2. If you don't believe me, it's 2 times 2 is 4, times 2 is 8, 16, 32, 64, 128, 256, 512, and we've blown past 120. So it doesn't work. So let's graph both sides. BRB, go on to Desmos. I'm back. So this thing, whoa, we got zoomed way out. This thing, here's a better explanation of why it was kind of just difficult to read or difficult to see. I mean, again, with this one being 35, it wouldn't have been that big a deal. But okay, the 4,200. I mean, take a look at this. It would have been tough to see that, oh, okay, I have confidence in the fact that the answer is 7 something because I can see that it's between 0 and 20, right? Down right there. But on the 500,000 or whatever, it's just a little bit difficult. The other thing I want to point out, and the reason that this is worth looking at, is if you don't type in y equals 120, then you would not get that line. It would not be there, and then you would have no answer because you wouldn't be able to figure that out. So there is a little bit of benefit to having practiced some of this. Let's see, when will the dough volume be that? And was it hours? Every hour. So 7.9 hours is the answer when x is 7.91 hours. Down here, let's do some solving. And guess what? We can solve these. So really, I think it's just they've returned to, hey, let's do some more practicing of solving. And then down here, who knows? We're going to have to do some rewriting for sure. Let's check this out. 125 is really 5 to the third power. Let's see, 5 to the third power raised to the x minus 1 power. And then this is just 5 to the 3x minus 2 power. So we are going to multiply those power to a power, right? So 3x minus 3. When does that equal 3x minus 2? If I subtract 3x from both sides, I get negative 3 equals negative 2. And that never happens because negative 3 doesn't equal negative 2. How about this one? 8 is really 2 to the third power raised to the 2x plus 1 power. And then this side, I'm just going to go ahead and distribute that 3 and get 6x plus 3. Also, let's distribute this 3 and we get 6x plus 3. 6x plus 3 here, 6x plus 3 here. That always equals each other. 20. 81 is really, let's see, 3, 9, 27, 81. 81 is really 3 to the fourth power raised to the 4x minus 2 power. So that's 3 to the 16x minus 8. And this is going to be 16x minus 8. Another all real numbers. And if you're like, wait, why is it all real numbers? Because over here, hopefully you saw it, because it was going to be 2 to that power, 2 to that power. The left side was literally the same as the right. And same thing here. Here was us doing that part. And then once I distribute here, I get 3 to the 16x minus 8, which again, those are the same. So there you go. Hey, we got compounding interest. So let me remind you what that equation looks like. Y equals, or your account equals, the principal amount times 1 plus the rate over n times n to the t power. And let's go ahead and talk about what these things are. This is your initial investment, also called the principal. It's the starting amount. All those three are kind of the same words. 1 is 1. Yay. R is the rate. It's the percentage. We want to write it, though, as a, that was supposed to say decimal, as a decimal. And then N is the number of times it compounds. And then T, years. So let's plug in what we've got. You deposit $750. Well, in my account, Y or A, doesn't matter, is $750. That is ugly. Let's try again. $750. That's not much better, but here we go. 1 plus it earns, so that's good, positive, 4%. I'm going to go ahead and change that to a decimal, because I said we wanted that 0.04, and it's going to compound yearly. Annual interest compounded yearly. That means just one time. So really this right here, number of times it compounds per year, I guess I should have said, right? Because if this is 1, how many times does that compound per year? 1 time. And so that N is actually here also, meaning it's here also. So there's 1, and then times T. So we didn't have to write that equation. However, they want us to answer how many years will it be when it equals $1,000. So we can do a little bit of the math to kind of get there. When does 1,000 equal 750 times 1 plus 0.04 to the t power? So we can divide by 1,000 if we really want to. I'm sorry, we could divide by 750. So if we divide by 750 on both sides, then that goes away. And let's see, this is 4/3. 1 plus 0.04 to the t power. So now, pause, go to Desmos, let's check it out. All right, here we go. We got the graph. There's the 4/3, there's the other one. And I just want to point out that 4% is not huge growth, so it is pretty slow growing growth. In fact, remember, this is in years, so like only after 40 years does this thing really appear to look like it's taking off. So anyway, after 7.33495 years, will you grow your $750 investment to $1,000? Does it say we need to round it? Nope. So we'll just go ahead and say 7.335 is our answer here. T equals 7.335 years. All right, so we're rewriting these so that we can solve them. I mean, I suppose you could just type this into Desmos as is. However, I think that we're going to be able to just solve this by hand. And really on your test, like once we eventually take the test on this, what that will be like is, hey, there'll be certain ones you can use Desmos on, but not all. So here we go. This is really 3 to the 1/5 power raised to the x power. And we can deal with that because power to a power is 3. I mean, we could call it x over 5, or you could call it 3 to the 1/5 x power, like that. And then the right side is, well, it's a base of 3, like that. So that's why I said, I'm pretty sure we could just solve this as it is. I'm going to choose the fraction equals that. So 1/5 x equals 3x minus 5. I'm now going to multiply the entire equation by 5, which means both sides get multiplied by 5. And this is now x equals 15x minus 25. Seems a little strange to do that, I know, but I did, okay? I guess I did that just to show you that, hey, we can deal with that. Or because maybe I don't like fractions either. Subtract 15 to get negative 14x equals negative 25. You divide both sides by 14, and you get x equals 25/14, which is a heck of an answer, right? And if you're like, well, what would have happened if we'd done it here? Okay, well, you subtract 3x, and you would have gotten negative 2 and 4/5 x equals negative 5. I mean, now we're going to have to do this. Negative 5 divided by negative 2 and 4/5, which is like this. Negative 5 divided by negative 14/5, which I don't know if you know how to divide by fractions, but what you do is you keep the first one, you flip this, and it would be 5/14 negative, and holy cow, we end up with the same answer. X is 25/14. Don't know if you saw that one coming or not. Let's move on to the last one. That is 2 to the 1/6 power raised to the 2x power. So this can be rewritten as 2 to the 1/3 x power. How come? Because 2/6 x can be written as 1/3. And over here on the right, this part is 2 to the 1/4 power raised to the x minus 3 power, and then you multiply those, and you get 2 to the 1/4 x minus 3/4 power. Well, just like we've been doing since the bases are equal, and that's what happened over here. Did I point that out? Right here, both of these bases were equal, and that's why we made those equal to each other. That's why we made them equal to each other there. So 1/3 x equals 1/4 x minus 3/4. If you liked me getting rid of fractions before, I'm going to multiply by 12 now. 12 on both sides. That's not to the 12th power, by the way. So this side is now 4x. This side is 3x minus 9, because the 4 goes into that 3 times, and 3 times 3 is 9. So we subtract x, and we subtract 3x to get x equals negative 9. And we are Dunskies. So that's the whole thing. Just under an hour to do all of that, to explain everything in great detail. I hope that if you have questions, you ask me about it. Please let me know how I can help. So yeah.